Okay, welcome back. What I'd like to do is I'd like to introduce a dear personal friend, an ASHRAE legend, past president, and he runs, I think, the best building science course in the university in the United States of America.
We're number three.
Okay, well, I think you're number one. No, in the United States.
That was my point.
Yeah, the 11th province.
Paris, Paris, the 11th province.
This is really bad if I'm laughing this hard this early, okay? Anyway, Bill runs a spectacular program at Penn State, and literally it is, I think, the best building science program that we have, and he's going to talk about something that everybody agrees on, which is indoor air quality. So please give a warm welcome to Bill Bahnfleth.
Yeah, thank you, Joe, and it's really great to be back to talk to this group of expert colleagues and peers. You may note that my title is different than what's in the program. It didn't get updated, and there's also an abstract that I won't read to you. I wanted to talk broadly about ventilation and air quality today, so I did switch things up a little bit, but we will be talking about ventilation and indoor air quality, not about operational carbon or something like that. I should also say before starting that I knew Eric Burnett as the director of our Housing Research Center at Penn State, and he was a great guy, and I can see how people like Joe and John turned out the way they did under his tutelage. I also wanted to say that John Straub is always a hard person to follow. He's probably a hard person to precede, but I will do my best to be at least informative, if not entertaining. So I start with my dad joke title: "To err is human, but is it the best way to control IAQ?" And to sort of give you my punchline before we get all of the details, I think that we're stuck in a paradigm of more and more outdoor air is the way to make indoor air quality better, and I think that's wrong in many ways. So I will make my case about that. I do want to thank John for showing that there may be subjects where we're even more confused than we are about indoor air quality. I want to start with a quote that I found in a document I downloaded on the way to the conference. This is from Joe Laverge from Belgium, who's a great building scientist over there, and he had at the beginning of a report written by someone else a quote from Andy Pursley a long time ago, who has been very involved in ventilation standards, that we design our ventilation for no particular reason, which is kind of a hard thing to hear coming from someone who's been the chair of ASHRAE Standard 62.1. But if you go on to read the details here, what he's saying is that much of our ventilation standards, many of them are shrouded in a veil of consensus fog. And I know from personal experience that a lot of the people who are on these committees aren't really all that keen on saying exactly how they came up with those numbers. They say, yeah, we looked at all the data and we have a method, but they're not going to tell you. And of course, that's one thing I'm not in favor of continuing to do. I think we need more transparency in our standards, and we need to take the consequences of showing what our methods are. So let's, without giving the whole case about why better indoor air quality is good, I mean, Joe down in Boston at Harvard, the other Boston Joe, has written 2 editions of a book on why that's important, and many others have as well over more than 20 years. Ventilation means dilution with outdoor air to most in the conventional wisdom. And why does that seem like a good thing to do? Well, there are lots of contaminants that have indoor sources. Building materials will emit various things. Indoor processes have emissions, and occupants, as we were discussing earlier, have emissions as well. And the consequences of exposure to these emissions are bad in a number of ways. Odors are unpleasant. We can have chronic toxicity if we're exposed to really harmful things. Some of them can cause increased incidence of cancer, and then there's productivity loss as well to throw in there. So the theory is, the belief is that outdoor air is fresh, so if we bring in a lot of it, we'll make the indoor air fresh too. It's a great theory. So I want to point out one important equation here before we go on to talk about whether more outdoor air is a good idea. This is the steady state concentration equation for a constant contaminant source, ASHRAE, emitting some volumetric amount of a contaminant. And we have in our ventilation air a concentration C0. And what we see here is that the increase above the ambient is S over Q, where Q is the ventilation air flow rate. So the more uncontaminated or lower contamination air we bring in, the lower our steady state concentration is going to be. And that sounds great until you start looking at what it means to try to improve indoor air quality. So what the implication of that equation is that we have exponentially diminishing returns for more outdoor air, and consequently exponentially increasing costs to condition the outdoor air. So if we start at some reference level, let's just say it's where we are today, and if we want to cut our indoor exposures down to 1/8 of what they are normally, it takes 8 times the outdoor air, and most systems can't even provide that much air, much less condition it. So it starts to look like maybe not such a great idea. And of course, the other thing is that outdoor air isn't fresh a lot of the time. And we used to like to show these pictures of places like Delhi in India and say, oh, isn't it awful that they've got such bad air quality there? But we're at a moderate level here, and I just came back from vacation in Minnesota, and we had air quality indexes of over 150 while we were up at the lake. You couldn't see across the 2-mile lake on a bad day. That was because of the way the wind blows. And this is what the US and Canada, our cherished 57th or 51st not state, looked a few days ago. I'm not on that program. I like them just the way they are. But you can see that wildfires are creating a huge area of really bad air quality, and wind currents are taking that all over the country. And that's why we've got an AQI in the 60s or 70s here in Westford today. So if you wake up with sand in your eyes, you stayed a long time at the clubhouse last night, or you're sensitive to PM. And this happens around the world. So you look at a map of Africa and the Middle East and Asia, and there's a lot of really bad air quality in outdoor air. So we really shouldn't be focusing on it for that reason. Another important definition to clarify for everyone, if you haven't thought about this or read about it much, is that ventilation does not mean outdoor air by definition. That's not actually what standards have meant when they discuss ventilation for a long time. So I've given the definitions of ventilation that you find in ASHRAE Standard 62.1 and 62.2 here, and both of them simply say that it's supplying air or removing air from a space to control air contaminant levels. So this doesn't rule out having recirculated air that's going to be cleaned in some way. A related concept is ventilation air, supply air that's outdoor air plus any recirculated air that's been treated for the purpose of maintaining acceptable IAQ. And I think that's really the key to the future, as we'll discuss as we go along here. So here's a typical multiple space, commercial type VAV air conditioning system. And you can see over there on the left-hand side that we have outdoor air, and we mix it with return air. And usually the return air volume is a lot larger than the outdoor air volume. So if we can remove contaminants from that, it helps us quite a bit. So recirculating systems can filter particles. That's the main thing we do, is have filters that will remove particles from the air, and the outdoor air will perhaps lower particulate levels, but also remove some of the contaminants that are of indoor origins. We can add other controls if we want to control gaseous contaminants to the conditioning of that return stream. Strangely, over all the history of minimum standards, we have not until very recently had any that tried to figure out what the combined effect of all the controls was. We have some ventilation, which actually we can do calculations to figure out what it's doing, but then we have a filter, and the filter has to have an efficiency of X or higher. Well, that doesn't tell me anything unless I know how much air is going through it and where it came from. So it's kind of a flaw in the existing standards that that's the way we do it. Recirculation does have that good quality of making it possible to remove more indoor contaminants faster, and to allow us to use air cleaners, and it increases economizer capacity. If we have a DOAS system, that's usually designed just for the minimum outdoor air. If we have a recirculating system that has 5 or 6 times the amount of supply airflow, then we have the ability to do economizer control in climates where it makes sense. And what's not so good is that multiple space circulation takes whatever is in one space and eventually spreads it out uniformly to all of the other spaces. So it's not really good at containing point source emissions. And also it increases the energy use, because fan power to move large quantities of air is more expensive than having part air and part refrigerant or water. So here's a simple little 2-zone example from one of my Penn State lectures. We've got 2 spaces, they've got the same area and volume, and we have a filter in the system, and we're going to assume that we initially have a contaminant released uniformly in the first zone, and there's none in the second zone. Then we're going to see what happens when we run a little transient process. And what we see in this figure is how concentration changes over time in zone 1 and zone 2 without a filter, and with a filter that removes 35% of the contaminant on a single pass. So the no filter release zone concentration is that black line with no symbols. It starts out at 100% and drops. And the second zone, no initial contaminant concentration, no filter, is the line with the blue circles. And you see that concentration increases rapidly due to the recirculation that's going into the supply air, and eventually we've got the same concentration. When you put a filter on this system, we get the same kind of behavior qualitatively, but note that both of those concentration profiles come down much more quickly to lower levels. And so if I didn't know that there was a filter in the system, I might infer that someone had just turned up the outdoor airflow a lot to dilute it, which again suggests that maybe we ought to be able to combine these things. And the way we do that is with concepts that go under various names, but the one we're talking about now is equivalent clean airflow, because that's what we called it when we wrote ASHRAE Standard 241 for infectious aerosols. So maybe this is a better way to do it. You can show that if you try hard enough, you can represent the effect of any air quality control in terms of an equivalent amount of dilution. So there's some amount of uncontaminated air, not necessarily outdoor air, but uncontaminated air, that would have the same effect. And so then we can add these things together when we're looking at the control of specific contaminants. And that makes it a lot easier, maybe not easy, but easier to do performance-based air quality control. Now in Standard 241, we were concerned about particles containing active pathogens. And so we called the required ventilation in that case ECAI, equivalent clean air for infection control. And we had a lot of arguments in the committee about whether we should put a subscript on it or not. And I said, well, yes, if we're just looking at this standard, we know that it's for controlling infectious aerosols, but I had this thought that we could generalize it. So we're going to need at least 3 different categories to be able to use this across indoor air quality standards. Gases would be one. That's going to be the most difficult. Particles probably easier because filtration is something we understand how to use pretty well, and then infectious aerosols. These concepts are actually getting some air in, no joke, in our ventilation committees. So a really simple example of how to determine an equivalent clean airflow, and this is really much like the clean air delivery rate that is the basis of AHAM standard AC1 for portable air cleaners. Got an example here where on the right-hand side, we have a space that has a source S in it, and we want to maintain a concentration C, and we're taking off a flow rate of air QF, which is the flow through a filter, and we put it through a filter with an efficiency of eta, and so some of the contaminant, but not all, is removed, and it goes back into the space. So we can imagine that there's an equivalent process on the right that's left that's dilution only, and so there's some QV, which is going to be our equivalent clean airflow that will achieve the same concentration. We'll assume that this is uncontaminated air. If it's going to be equivalent clean air, we've got to set C naught to 0. And so it's really easy to show that the equivalent clean airflow, before you try to account for air distribution effects, is simply the flow rate through the filter multiplied by the filter efficiency. Gets harder to do when you're looking at something like a UV system in this space, where there's not actually any airflow through a device. You're simply putting energy into the air, but it can still be done. All right, so that's an important concept that I hope we can promote. One of the big questions is always how much ventilation, and we could talk endlessly about how much, and there's different values for different spaces, but I'll try to put a conceptual framework around this. One of the important things is what are we trying to accomplish with ventilation? Ventilation is really all about controlling air quality for some purpose, and if you went back to the early 19th century, the thinking was, well, people are using up oxygen and we've got to replace that. And we initially had, from Treadgold, really low at 4 CFM per person recommendations for ventilation. But then Billings in the US and Fluga in Germany, and it's a serious omission from this figure from the paper that I got it from, but Florence Nightingale recognized that people had better outcomes in healthcare facilities if they had high levels of ventilation. And so when you got to the late 19th century, the recommendation went from 4 CFM per person up to 30, which is a number we've heard again recently during the COVID pandemic and after. And this was actually picked up by ASHVE, ASHRAE's predecessor organization, in 1914 in a model ventilation code. And by 1922, 22 states had 30 CFM per person as their ventilation standard. But there started to be some pushback on that. That's a lot of air, and maybe it's not accomplishing what we want it to do, and perhaps we're starting to become more concerned about the energy use. And so Yaglu at Harvard School of Public Health did some research on ventilation, and his belief was that really if we were ventilating enough to control odors, that would be all it took. And so that brought the ventilation rates back down to 10 CFM per person, and they more or less stayed there through the initial publication of ASHRAE Standard 62.1. We got to the point, though, when the energy crisis occurred, that there was a lot of pressure to reduce outdoor airflows again. And for a short while, ASHRAE had recommended ventilation rates and minimum acceptable ventilation rates. And guess which ones everybody picked? So it didn't cause sick building syndrome, as some have suggested, but it certainly didn't help. And the reason I say it didn't cause sick building syndrome is that sick building syndrome had been identified as a problem years before the ventilation rates in the codes dropped down to that level. We were just making sure that it was a problem, I guess, when we did that. But it only lasted for one edition of Standard 62.1, and then we got back to where we are today at about 15 CFM per person after smoking was taken out of the standard. It no longer will cover smoking spaces. So I think the lesson here is that we've never really been able to decide as an industry or as a society what we're trying to do with ventilation, and we need to come to a consensus on that based on the evidence that we have now. So let's leave that point for a moment and go to another one that's important for the development of standards and how much should we ventilate. And that is to note that ventilation is only one of the ways we have to improve indoor air quality. I think everyone knows these things, but it's good to look at them once in a while. On the left-hand side, we have the Swiss cheese analogy of reason, which wasn't, again, invented during COVID. It was in a paper published in 2000, Human Error Models and Management, which is a really interesting read. The more different modes of control we have, the more likely we are to protect ourselves from a given hazard. And then over on the right-hand side, also very important, is the NIOSH hierarchy of controls, which embodies the important point that getting rid of sources is really the most important thing we can do, or substituting less harmful sources. And then after we've done all of that, then we have to look at what we can do with other controls like ventilation and filtration and air cleaning and things that are even more significant than that. I've been amused for quite a while that both ASHRAE standards 62.1 and 62.2 published addenda to change one word in the title of the standards, but it really, I think, fits in with this point. On the left, we have the cover of ASHRAE Standard 62.1 2019, and the title is Ventilation for Acceptable Indoor Air Quality. And on the right, we have the title of the current version, Ventilation and Acceptable Indoor Air Quality. And I think this is maybe subliminal, but it's important that ventilation does some things. But if you actually take the time to read the whole standard, you'll find that there is a lot of other important good stuff in Standard 62.1 and 62.2 about how you go about maintaining acceptable indoor air quality. And of course, one of the things that I think is really important and neglected is that there are chapters on operation and maintenance in those standards. And unfortunately, that's where they have stayed, because what goes into the codes is only the design requirements, the prescriptive design requirements for ventilation rates. So if we look at what the goal has been in standards, for the most part, perception and safety have been the things that we focus on for almost 100 years in non-healthcare facilities. Safety, and I'm very particular in choosing that word because I don't think it's health. I mean, we're trying to prevent certain harms with the standards, but not to promote what we would consider a current definition of health, which is more than simply not getting cancer due to airborne exposures over your lifetime or other problems. So the definition of acceptable indoor air quality in ASHRAE Standard 62.1 is shown there, and you can see these two aspects of IAQ that are prominent. No known contaminants at harmful concentrations, that generally means lifetime exposure limits as determined by authorities, and the other part is a substantial majority exposed, not express dissatisfaction. And the graph on the right comes from the work of Fanger in Denmark mainly, but others as well. And you can see that if our goal is 80% or more not dissatisfied, then we're at about 7.5 liters per second per person, which is about 15 CFM. And apparently that's considered to cover the other part of the definition as well, because we don't have a lot of spaces for which we have much higher per person flow rates than that. So if we look at these current standards a little bit, starting with non-residential, ASHRAE standard 62.1 has two procedures in it. One is called the ventilation rate procedure. It's prescriptive, and it's what almost everyone uses. And it has over 100 space types for which per person outdoor airflow and per unit floor area airflow are specified. So to get started, it's a pretty simple process of counting heads and measuring the size of a room, and that will give you the initial uncorrected breathing zone ventilation rate. You can see a little example of what's in the main table for that in standard 62.1. You should use actual head counts, but if you don't know it, there's a default occupancy. Another interesting thing here that I'll mention, although I'm not going to say much about it, is that this air class is an important improvement. You know, one of the principles of healthcare ventilation is clean to less clean. And so a while ago, standard 62.1 established classes for air that had been put into spaces. And if it's class 1, that's good, and you can recirculate it. 2, you can recirculate it with some restrictions, and eventually you get to 4, and that must be exhausted. So, you know, this is another one of those examples that there's a lot in here that goes beyond just how many CFM do I need. There's also a performance procedure that's been in the standard for a long time. It was justifiably neglected for decades, because it used to say that the user of the standard had to identify the contaminants of concern and what their safe levels were, and then do mass flow calculations to figure out how much ventilation was needed. And then, of course, they would be on the hook if things didn't work out. So there was a total redo of this a few years ago, and now there are 14 chemicals and 3 mixtures of so-called design compounds and PM 2.5 that are, for which limits are set. There's a table in the standard that gives those limits. So the designer still has to figure out how much ventilation or other type of control you need. This is a process or a procedure that would allow you to use air cleaners. And then when you're done, you have to do what is called objective verification, which means you go into the building after it's finished and measure to see that you've met all of those limits. And there's also subjective verification, which means you've still got to satisfy the 80% not dissatisfied criterion. So it's the same definition of acceptability, but if you are good at doing this, you may be able to come up with a lower energy building by using alternatives to more outdoor air. So here's the table on the left of the design compounds in PM 2.5. You can see that we owe California most of the design limits. There's a couple from 3 from the EPA NACs in there, and a couple of German standards as well. But so this is what you would have to do post-occupancy, and the mixtures below are shown. They're just combinations of those. For the mixtures, we use the familiar way of taking the ratio of the concentration to the design limit for each contaminant, and the sum of all of those has to be less than 1 in order to comply. So that's there. It's a big improvement, but I have to say that 18 things that you have to comply with is a lot, especially if you're going to think about maybe measuring some of them real time. And that's where I think some interesting work has been done that you should know about. In residential standards, we have pretty much the same definition of acceptability that we have in standard 62.1. It's almost word for word, except that they don't put the 80% in there. It's a substantial majority. So we have a contribution that's based on the floor area, and a contribution that's based on the number of occupants, but the way you determine the number of occupants is by counting bedrooms. So if you look at the equation there, the total is 0.3 times the floor area in square feet. So it's 0.3 CFM per square foot, and 7.5 times the number of bedrooms plus one. So that's like mom and dad in one bedroom and one person in each of the others is how you would get to that. So the minimum is 2, and obviously it's 7.5 CFM per person. And when you add all that together, you're probably getting close to our 15 CFM per person total. And this is for the whole dwelling, but it should be distributed uniformly if you can. Interestingly, there's a credit for infiltration that you can use to reduce the amount of outdoor that you have to supply through your outdoor air system. I found it kind of interesting that standard 62.2, in many ways is more technical and complicated than 62.1, and yet it's intended for the residential market. But so be it. At least they've taken this equation and reduced it to tables, so you can look up the floor area of your house and count the number of bedrooms and figure out how many CFM you need. I have a pretty small house, about 1,400 square feet on a finished basement, and we've got 3 bedrooms, so that says we need about 75 CFM for the whole dwelling. So there have been some recent addenda to 62.2 that I think are, and 62.1 that are quite valuable. There's an addendum for 62.2 that's looking at the use of equivalent clean air as a way of complying. There's a new indoor air quality procedure for 62.2 that's under consideration, but it's different and in a lot of ways better. And I'm going to talk about where that came from in a little bit. And they've also already developed an informative appendix, so non-binding, that deals with how you would apply ASHRAE standard 241 to a residential building. That's not in the 22 version. I think it'll be in the 25 publication that comes out this year. So a few observations on the status quo, I suppose, in addition to all of the other observations I've already made. I think we know what the rationale is. At a high level, we have qualitatively what the standards are trying to do, but the quantitative details are hard to dig out sometimes, if they even exist. And ironically, from my survey of standards and their evidence basis, it turns out that healthcare has the worst standards of all. That they're using mostly empirical air change rates that came from the mid-20th century. And I'll say more about that a little bit later too. I think that we're at an interesting point in time that we've gotten to where there is quite a bit of interest among the public, not just the expert community, that we should try to raise the bar on what we define as acceptable. I think part of that is more transparency on the basis for standards. We should put that basis out to be criticized and improved by debate. I think we should be moving towards performance or evidence-based prescriptive approaches, and we're getting to where that's more feasible. Expanding requirements to new areas like health and productivity, and I could add resilience here as well, is a strong interest of many, and a bigger role for air cleaning and disinfection. For a long time, it seems that all air cleaners except for mechanical filters were deprecated, and I think we're starting to see that maybe there actually is potential for them if we don't just charge blindly into using them when we don't really know enough about what they do. So let's now move to looking at some interesting research that I think is informing the developing approach to standards and a new rationale. I want to start with a historical paper just to make sure I acknowledge all the sources. A few years ago, Logue et al. At Lawrence Berkeley National Lab did a really interesting study to develop a new method for identifying the harm caused by contaminants. So their goal wasn't to set new standards, but to figure out which contaminants were causing harm and to quantify how much they were causing, and doing it in terms of disability-adjusted life years. which is a pretty well accepted practice that works well if we have good data on the consequences of, say, toxic or carcinogenic exposures, but it doesn't work so well for other things. But for what they were trying to do, I think it was a good approach. And so their analysis found that there was a really pretty small number of contaminants that in residential buildings were producing most of the harm. This is a figure from that paper, and I've made a little box at the upper left-hand corner to show what looked like the worst contaminants of the many that they looked at. Note that that's a log scale on the vertical axis, so every time you go up one tick, that's another order of magnitude. So all of those things to the right of ozone are orders of magnitude lower than PM. And this was also, I think, the first paper I was aware of that clearly showed that the main thing we have to be concerned about is exposure to particulate matter. See, PM 2.5 is up there. SHS, secondhand smoke, that's an issue when people smoke indoors, but then we've got other things you would expect to find being serious concerns. Formaldehyde, radon, and they have different values for smokers and non-smokers. Yes? Dolly lost per 100,000 persons per year, a disability adjusted life year. So you start with the life expectancy of a person with no adverse effects. And then if you have, let's say, tox or epi data on something that causes some kind of disease, you can use that data to determine how many years that will take off of life expectancy. But it can also be done, and I'm not an expert on doing the nuts and bolts of these calculations, it can be done for morbidity as well as mortality. It's not just shortened life expectancy, it's reduced quality of life where there's some kind of disability caused by an exposure. I always get a little bit worried when we boil lots of things down to trade-offs. So you got to be careful about the bounds you put around it. Bjørn Olsen, my colleague from Denmark, former ASHRAE president, used to say about one of the green building standards, you know, do you want better indoor air quality or a bowl of apples in the lobby? You know, you can get the same point for doing, or of course the bicycle rack. Yeah, I know someone who did a building in, I think it was Montana or Wyoming, and they got a lead point for a hitching post. So, you know, you got to be creative when you're applying these standards. All right, so Logue et al. Was done at Lawrence Berkeley National Lab, and Max Sherman was involved in that. And he eventually, through some strange series of events, got connected with Ben Jones, a professor at University of Nottingham. And so recently we've had some really good work done by a PhD student of Jones, with Sherman being involved in it. So I've included the DOIs for these papers in case anyone wants to look them up. You may not want to read all the details, but the bottom lines are pretty interesting. So Morantes et al. Kind of replicated the Logue study with some differences in methodology. And they started out with over 300 indoor air contaminants, known indoor air contaminants. And they eventually found a small number that had enough data to do what they wanted to do. And they started by, for each contaminant, identifying a harm index. And actually, I think that should have been 45, not 25, but who's counting? The harm index was the dollies caused per year per some number of people for a unit of exposure. So if you get this harm index, and then you have the actual concentration, then you can get the dollies for that contaminant in a particular application. And so they got results that were pretty similar to Logue et al. And this is now being used as the basis for the proposed indoor air quality procedure for standard 62.2. And I'm pretty sure that it's 45, not 25, because as you can see from this figure, there are 6 contaminants that are responsible for 99% of the harm using this methodology, and the other 39 that they screened collectively only accounted for 1%. And again, you see that PM 2.5 is the greatest at 67% of the harm, and right next to it is coarse particulate matter. So particles together, for the assumptions that they made, are over 80%. And the other things, nitrogen dioxide, if you have indoor combustion for cooking, and formaldehyde and radon and ozone are the others. So this makes me happy because it starts to look like maybe there's a practical way to do this. Yes?
Included in any of the PMs, like it was just a human that they're not count, or is the data not good enough to put them?
No, I think there's data. I imagine that since they were thinking in terms of what to do with standard 62.2 and kind of written smoking out of the ASHRAE standards, at least, as being unsafe, maybe that's why they didn't include it. But I would go back to the Logue paper, I think, to look at the risk there.
But I found there's a lot of people smoking things that aren't tobacco. So the secondhand smoke is still there.
I'm shocked. Shocked, sir.
Ending hot because we're telling that people don't smoke.
Yeah, well, you can get it in a can, you know. I was just in Minnesota. Certain beverages are legal there that aren't in Pennsylvania. All right, so this is really good stuff, and one of, I think, the few things to come along in recent times that's really created a lot of enthusiasm. And again, just within days of coming here, I got the pre-proof of another paper by the same group where they looked at office buildings. So it's really the same approach applied to a different type of building. So they have a different profile of contaminants that you find there in different concentrations. And they found that there were only 4 contaminants amongst the hundreds that they started out with that were responsible for 99% of the harm, more than that. And this is now being considered by a subcommittee of ASHRAE Standard 62.1 as a possible way of updating the indoor air quality procedure to make it more practical and useful. So again, PM 2.5, formaldehyde, ozone, and coarse PM are the main things. So you got a good particle sensor, that's getting to be affordable. Formaldehyde's not cheap. Ozone and maybe you're done, maybe. But again, this is one paper by one group, and I'm always reluctant to go along with the idea that somebody did a nice piece of research, so we should change all of our standards right now. We need to vet these things and to make sure that these are robust findings. So as you can see, I think dollies as a metric perhaps aren't the answer to all of our prayers, but they certainly have a role to play in our thinking about standards that are more evidence-based and quantitative. I mentioned some of these concerns already, that the trade-offs can be tricky, that you can have a very imprecise process for determining dollies. Somebody asked at some point, especially for things that aren't backed up by, say, toxicity data, to make a guesstimate of what the impact is. Suppose we go off in the direction of we want to use this kind of approach for productivity. How do you come up with the quality years lost for productivity? They're probably pretty smudgy. But the good thing is that this work so far has suggested that the list of contaminants that we actually have to pay attention to for control may be a lot smaller than we thought. And I don't think that there's really this kind of a rigorous basis behind the list of contaminants in the indoor air quality procedure right now that ASHRAE is using. All right, so let's move on from the minimum air quality standards to resilience standards. John mentioned resilience this morning as being a concept that's getting a lot of discussion these days. A lot of people are discussing resiliency, which just makes my flesh crawl, but that why is totally unnecessary. So I'm trying to promote resilience. So the goal here is to extend our standards to account for conditions that aren't normal. Maybe we don't think about it enough, but all of our building codes that are based on, say, the ASHRAE 2.1 and 2 standards, that's really ordinary air quality, assuming that you've got outdoor air of sufficient quality and assuming that we're not really concerned about things like there's a pandemic going on. You may have someone in your space who's infected with a disease that you're not prepared to ward off with your immune system, and so there's a high risk you could have a very serious consequence. So we are mainly concerned about infectious aerosols and also wildfire smoke. So for infectious aerosols, we developed the standard 241. I gave a full talk just on it a couple of years ago, so I won't go through all the details, but it was developed at breakneck speed and published in 2023 after 4 months of development. We're currently in the process of going through a couple hundred public review comments that we got. So we're trying to get it ANSI certification by next year. So we are working hard on it. So this standard only applies during what we call infection risk management mode, or periods when there's a heightened concern about infection. We haven't established exactly how that's done, but if you look at the current summer incidence of diseases that have been in the news about COVID and RSV and others, right now the level is probably pretty low. And if we were actually making a decision about do we need to do all of that here today, maybe some would say we don't need to, but there are others who feel we should just be operating at a much higher level of protection all the time because there's always some risk. That's an issue that we're working on to try to improve future versions of the standard. So what this standard specifies are equivalent clean airflow quantities for infection control. There's no requirement associated with outdoor air except that you have to meet whatever your base acceptable indoor air quality standard is. So if you've got a code that's based on standard 62.1 or 62.2 or 170, that defines your minimum outdoor air. We don't say anything about that. We have worked hard in this standard to allow air cleaners to be considered for use. We don't support them or endorse them. A few types are named in the standard, but the only objective here was to create a level playing field. So put in test requirements for performance so that you have to report what this technology does, and some safety requirements so that you have to clear in order to be usable. And the basis of this standard is population level risk assessment, very rigorous. We went through a Monte Carlo modeling procedure to come up with the ECAI values. And to my point about transparency, we've recently published all of the details of the model in a paper that you can now download. This is an open publication, and it has every parameter in it. You know, for example, probability of infection, 0.1 for a 1 hour exposure, and we have the community incidence rates that are assumed, 3% in healthcare facilities, 1% for all others, and so on. So you can read all of that. As Ben Jones likes to say, as he was one of the main developers of this model, so all models are wrong, but some models are useful. That's our theory here, because we use the best available knowledge. This flow diagram illustrates how complicated the process to calculate one equivalent clean airflow value was. The blue items are assumptions. What's the community infection rate, the exposure time, and the probability of infections we want to achieve. Everything in red was based on SARS-CoV-2 because we were in a hurry and that's the data we had. We need to generalize that now. And everything in the green box is a parameter for which there is a distribution. That we know of super spreader individuals who emit far more infectious aerosol than other people. So for all of those variables, we did Monte Carlo modeling where you sample the assumed distributions to get cases, how many infectors are present, what is their emission rate, and so on. And we did that, I think, with a 95% confidence interval in a Monte Carlo model. All right, so we get these ECA values that depend on the space type and how many people are there and what they're doing, and we don't have the coverage of standard 62.1, but there are 7 occupancy categories and 25 space types for which values were calculated. And these clean airflow rates vary from things that look pretty typical to things that might frighten you, 20 to 90 CFM per person. But remember, these are equivalent clean airflow values. So we're not talking about 90 CFM per person of outdoor air. And also the standard allows you, when you're operating in emergency mode, to simply reduce population to match what you're able to provide. So in this space, today, if we cut the population back to, I calculated yesterday, 136, we would actually still comply with 241. So it's very flexible and based on a rigorous and transparent risk assessment. Now, this is the table that has all of those values. I don't think I'll dwell on that. You can see that perhaps, though, that a few facility types like restaurants are pretty high and others are quite low. So one of the things that has really driven me nuts for years, and I'll say more about it, is the diversity of units and approaches that we have for indoor air quality. And so here's a little comparison of outdoor air in standard 62.1 and the CDC 5 air changes per hour recommendation, and what we would do with standard 241 for an office, a classroom, and a restaurant. So I put the standard 62.1 data up in the table at the upper right. The bottom is the one to look at. The default occupancy, 62.1 CFM per person, are in the first column, and they range from 10 to 17. And ASHRAE 241 per person numbers range from 30 to 60, but notice that 30 matches up with 17 and 60 matches up with 10. So they came out quite differently. And then air change rates using the 241 equivalent clean airflows with an 8-foot ceiling, we've got air change rates from 1.1 to 31.5. And the point I want to make here is that we did the calculations to show that the risk of infection is the same across all of these different space types. And this demonstrates how poor a single air change rate is at telling us what we need to do. 5 is way too much for an office. It's way too much for your home. Calculate what the airflow rate would be for your house at 5 air changes per hour, but it's not enough for a restaurant. So I think we're showing here that we can do better than we have done with some of these recommendations. So now let's look at wildfire smoke briefly, and I didn't chair the development of this standard, so I don't have as much to say about it. You're probably glad to hear, but Guideline 44 was published recently by ASHRAE, and this is not a code-intended standard. It's advice, best practices, but you can use it to design controls for smoke. It's for commercial, institutional, healthcare, and multi-unit residential buildings. And there's a prescriptive approach, and there's also a performance-based approach that requires you to do calculations. And it mainly focuses on pressurization and on filtration of outdoor air. So just to give you a glimpse of what's in it, there's a section on design calculations that involves using that ugly equation there, number one, which shows you what concentration you get for a combination of parameters that includes the outdoor PM level and your filter efficiency and a lot of other things. So you can use this as a design equation to determine what filter efficiency you need. But there's an easier way to do it as well. I recommend this to you if you're concerned about protecting buildings from wildfire smoke. All right, so there's another thing I want to talk about just briefly. I could go on for a long time about this, is air distribution. We spent a lot of time thinking about how many CFM do we need to put into a space that's well mixed, assuming that all of that air gets to where it wants to go. You know, if I put a vent on the wall over here and had 10 CFM coming through it, how much of that do you think the folks in the corners of the room or in the royal box over there would get? Aside from that, Mrs. Lincoln, how did you like the play? So this is really important, but we're not doing a great job with it yet. Now, we assume perfect mixing in our standards, and then we try to tweak it to make it work for the way real buildings are. So you'll find in standard 62.1 a ventilation effectiveness table that you can use at your peril. There are a lot of problems with it. I don't think even the committee believes what's in it, but they have it there for you to use. Ventilation effectiveness is going to depend a lot on the application, and the details of air distribution matter. I didn't include all of my figures from my COVID talks about how air currents were really clearly responsible for lots of infections. A restaurant with VRF cassettes on the ceiling, and they were creating, at the point where their airflows came together, a really high velocity flow of air, and the only people who got infected were the people who were in that airstream that was kind of originating where the infected person was. And we've seen the church in Australia where I think it was the choir director or the musician was infected, and you can see the pattern of infections that go from the choir loft to where the air patterns were. So we've got to be concerned about this, and we're kind of kidding ourselves if we think that just dumping the right number of CFM or liters per second into the air is going to get the job done for us. Unfortunately, we don't believe CFD most of the time, and we can't afford to do this for every space experimentally. So it's an area that needs a lot of work. So let's move on from that to a little more about air cleaners. And I think it's really good to see that they're getting the attention that they deserve, which is unpleasant, I think, for air cleaner manufacturers in some ways. But this is the only way in to standards and into performance-based air quality, as I think we would like to have it, is for them to show that they work and that they're safe. COVID had a really overheated air cleaner market, and what we found was, first of all, that at least at the beginning of the pandemic, most of the claims of performance didn't have much evidence behind them. They're mostly just the manufacturers say so, their observations. Their clients have said, yeah, we got it and your quality is great, but they didn't really have data. Reporting of performance tests was highly misleading. We had data being reported in terms of equivalent air changes per hour, but the air change rate was based on a 100 cubic foot box. So it was actually a pretty low cleaner delivery rate, or they would say 99.9% reduction in 3 hours with the technology on in a chamber. It would be like 99.5% in 3 hours with the technology off because of natural losses. So there was all sorts of shenanigans going on there that we're trying to stop by writing better standards. And the only safety testing that was being done was for ozone production, because in the codes, there was a zero ozone emission requirement, but none of the other things that might happen from indoor chemistry. So there have been some good outcomes. We've had a new chamber test method that's been published by ASHRAE, standard 185.3, that is going to really improve our ability to characterize air cleaners. There's research going on in academic institutions and in government agencies in some countries for all air cleaner types. And a really encouraging thing for me is that ASTM is working on a test standard for chemical emissions that will be very useful when it's done. The paper that I've shown there alongside of this text is an article written by some of the people involved in developing that standard that describes the methodology. Basically, they've got a cocktail of gases that are commonly found in indoor environments. And so you seed a chamber with that, and then you turn on the technology and you see what happens. And they're looking for VOCs and for secondary organic aerosols and that sort of thing. So here's some figures from that article by Link et al. This is mainly people at NIST. And in this one, they are looking at mostly UV-based products. So GUV means essentially upper room or whole room irradiation systems. PECO and PCO use catalysts and are really kind of a different technology, even though they use UV. And there's also an electrostatic precipitator there. And what you see is that for most of these, there was some, at least small, increase in VOCs, except for the ESP. That was the only one for which they decreased. And the others show details for VOC generation for the different technologies. Those are the ones in the upper right. And then particle generation is shown in the block in the middle. Interestingly, 222 nanometer UVC, which is being really promoted hard for whole room irradiation, seems to produce more byproducts than our old friend 254, more particles and more ozone. So I think we probably could have agreed a long time ago that this is going to happen. This is just photolysis that we're seeing, but no one had taken the time to look at it. I think the question is, what do we do with that information? Do we say, okay, we can't use these because they produce byproducts? My question is, should we stop using UV air, using outdoor air because it's full of ozone? And outdoor ozone levels are higher than indoors, and our main source of ozone is from outdoor air, and to perhaps show some evidence of that. Here's a study that was done at the University of Colorado, and this is modeling again. This was Peng et al. And Jose Jimenez, whose name you may know from the pandemic. So they looked at ventilation-only 254 nanometer UVC and 222 nanometer UVC at 3 different air change rates. So 0.3 air changes per hour low. That may be actually getting close to normal ventilation for some spaces. 3 air changes per hour is medium, and 9 is high. So in every one of these blocks you see on this figure, we've got low, medium, and high groups that have no UVC 254 or 222 going from left to right. And expectedly, the UV worked really well on SARS-CoV-2. So in the upper left-hand corner there, you see that it was effective. The rest of these blocks show what happened with several secondary contaminants, and I've marked a couple of them there that I think are important. The paper doesn't comment on this so much, but I think it's quite interesting. If you look at ozone levels at the different ventilation rates, you see that there's a very strong increase in ozone with increase in outdoor air, and it's much greater than the difference between no UV and UV. So I'm asking, why are we so concerned about 222 producing ozone and we're not concerned about this? I'm not saying we shouldn't be concerned about the ozone production from UV, but we've got to start looking at everything. Ventilation can't take a pass either, and this goes back to my point that outdoor air isn't fresh much of the time. So where I think that, yeah, go ahead. I'd have to go back to the manuscript. Sorry, it's modeling, and also I don't think that they were trying to use extreme outdoor air conditions. I think it was what they would consider to be acceptable outdoor air. But let me follow up on that. I've got time to answer that question later on in the conference here. So what I was going to say was, the question is, if there's a significant benefit from a technology and a certain amount of potential harm, do we just say you can't use it, or do we try to figure out how to mitigate that to an acceptable level? So right now, you couldn't use 222 in a building that was following ASHRAE standard 62.1. I want to say I'm not shilling for the UV guys, but that there are technologies that may be useful that are being shut out because of this. Okay, so now I get to beat up on units for a little while. So do ventilation units matter? Well, if they didn't, why would I put this slide in my talk? I just want to say a little bit about air change rates versus what I would call absolute flow rates in units like cubic feet per minute or liters per second. It's really an important difference, because an air change rate is relative. It's flow rate measured in room volumes per unit time. It's also not actual replacement of air. So we got two problems here. One is it's a relative unit, and people don't understand that some of the time. And it also, an air change doesn't mean that you're changing all of the air. If you have mixing going on in a space, then you're only actually removing about 37% with every air change. And yet, air change rates are the basis of healthcare standards, they're the basis of laboratory ventilation, and also animal facilities. And I was really unhappy that during the COVID-19 pandemic, people started looking at healthcare standards and saying, oh, well, we should have an air change rate of X because that's what's in the healthcare standard, not knowing that the healthcare standard really was full of numbers that were at best empirical. So air change rates became very common to the point that CDC recommended 5 air changes per hour of clean air delivery as their standard back in, the recommendation back in 2023. An interesting thing, if you're doing some math with this, is that you can't directly determine a contaminant concentration simply from an air change rate. That you got a source and that has a certain strength. Until you take the air change rate and turn it into an actual airflow, you don't know what the maximum is going to be. What they're useful for is defining the length of a transient period. So if you introduced a source into a space, you could use the air change rate to figure out how long it would take to come up to its maximum concentration, or how long it would take to clear a contaminated space. But if you're going to do the concentration calculation, you have to use the actual flow rate. So absolute flow rates are flow in units like CFM and liters per second per unit of something. Could be per floor area, per person, as we've seen. And this is the basis of residential and non-residential standards. And I think that's why, because it just makes sense to focus on dilution in the worst case to maintain an acceptable concentration. So here is the math. The equation on the upper left is what you get when you do a transient calculation of concentration. And here CSS stands for the steady state concentration, and C at time t and C0 are at the beginning and end of some period. And those are dependent in an exponential way on the actual flow rate of clean air divided by the volume of the space, and that happens to be the air change rate. So I've replaced Q over V with air change rate in the second equation. But you need the steady state concentration to know what the actual concentration is, and we get that from the equation on the right that we've already seen. The figure here shows how air changes work. We've got initially 100% of the dimensionless concentrations at the left-hand side of the upper left equation. And if we have 1 air change per hour, the concentration comes down slowly towards 0. And if we have 3 air changes, it comes down more quickly. And every time you have an air change, you reduce the concentration by 63%. So I've marked 1 air change up to the point where we have the concentration of the 1 air change case. That's then 37% of what we started out with. And if you just go horizontally to where that line intersects the 3 air change per hour curve, you find that we have 37% of what we started with after a third of an hour. So that's after 1 air change. All right, so that's how they work, and these are the sorts of things that air change rates are good for. They're not good as a general ventilation specification. So very interestingly, ASHRAE sponsored a research project to investigate the evidence for air change rates in its standards. What's interesting is that they did this in 2023, and the first publication of ASHRAE Standard 170, which is their healthcare standard that's based on air change rates, was in 2008. So at some point after more than a decade, they said, maybe we should figure out, whether there's any evidence for these things. And I've got a few pithy quotes from the report. They're not encouraging. The only robust evidence is that ventilation can be used to control thermal comfort and therefore minimize distraction and fatigue among caregivers, not asepsis. Unfortunately, a single optimal air change rate was not identified for any healthcare space. And then finally, they discuss how air change rates are probably going away, but to John's point earlier, they say, and I love this quote, given the observed pace of change for the HVAC industry, air change rates days are numbered, but it's likely a large number. So there you go. And then no discussion of ventilation would be complete without getting irritated about the uses and misuses of carbon dioxide. So I'll ask here, what about carbon dioxide? For details, I'll refer everyone to the ASHRAE position document on indoor carbon dioxide, which is a very nice document, and it covers all of the topics that you see there. The point of these is to come up with positions that can be used in advocacy and also recommendations for research and those sorts of things. I've paraphrased a few of the positions. Important one, CO2 is simply not an accurate overall indicator of indoor air quality, but if you know what you're doing, it can be useful. The problem is that there are a lot of people with AeroNet 4s who have no idea what they're doing, and they're getting concerned about things or getting misled about what those data mean. For evaluating ventilation rates, indoor-outdoor CO2 concentration is essentially using a tracer gas, and it's only accurate if you know the parameters of the measurement. So you wouldn't do a tracer gas test without knowing what your assumptions were and what the inputs were to it. So you can use it for that, but you can also come up with misleading results, partly because CO2 concentrations are often not steady state in a space. If population's changing, ventilation is changing. There's evidence of the effects of CO2 at typical indoor concentrations on health, well-being, learning, sleep, and work performance. but it's mixed. The conclusion here was that, yeah, there's a lot of developing evidence, but not enough to change standards. And this is really, an important thing to keep in mind, that some good research will not inevitably lead to better standards. Sometimes good research just tells you we need to do more so that we're certain enough of what we're finding to improve standards. In theory, there is a connection between CO2 concentration and airborne infection risk, the so-called rebreathed air fraction, but it's really hard to apply accurately. Your risk depends on a lot of things besides just the ventilation rate, like is there a super spreader in the room with you, or someone with mild infection, or nobody. So it's an interesting concept, but it's more theory than something I think you can use in practice. And of course, I think everyone would agree, sensor characteristics and placement are critical for control when you're using CO2. So ASHRAE standard 62.1 has finally caved in and now provides data for supporting the use of CO2-based demand control. You can see my parenthetical there. So what you have here is the maximum increase above the ambient concentration for different types of spaces. And all this is doing is giving you a number that will return the same ventilation rate that you would have gotten if you had done the prescriptive calculation. There's some spaces for which they didn't think that could be done, but for others, they could. If you're using this for a recirculating system, then these numbers don't work. You would have to reference them to what's in the supply air, because they're increments that represent how much additional dilution there is. One more thing I don't like about CO2 concentrations as a way of controlling ventilation is that ever since we split the ventilation into a room component and a personal component, a constant CO2 concentration will no longer give you the correct ventilation rate, because the room component has to be maintained all of the time, and the part you can turn down is the occupant component. So what you're getting is a smaller and smaller amount of CO2 generation as the occupancy decreases from maximum. So what should be happening is, because of that constant amount for the floor, is that the set point should be declining. So what we see here in this example is a lecture classroom, and at its full occupancy, it should be at about 1,700 ppm. I know that's a number that shocks people too. We see recommendations that indoor CO2 concentration should be under 800 ppm. If you go through standard 62.1, you'll find almost up to 2,000 like this, but also some that are lower than 800, even down towards 600. It mostly depends on the occupant density. So that black curve, as the occupancy decreases, shows you what the CO2 concentration would be if we had the correct ventilation rate. And obviously, as we go to nobody in the room, it's going to go to whatever the ambient is. It's moving towards 500 ppm. So this, you can only crudely approximate this in a real space. Okay, I think I'm going to make it, Joe. So now we're to the wrap up here to try to summarize some of the points from this pretty diverse agenda. The status quo is still dominated by prescriptive air supply. The objectives of ventilation haven't changed a whole lot in 50 years. If you go back further than that, we see some differences. There's some evidence behind some outdoor air requirements, but not others. And there's a lot of interest in improving IAQ, but more outdoor air is not the way to do it. But there's more. All right, so some promising trends. Standards and guidelines for extreme events, not just because I've been involved in one of them, but I think this is a direction we need to go. And I would actually like to see the things that are described in those standards just getting into our general IAQ standards. I think, why shouldn't a minimum IAQ standard include resilience as well to some extent. The equivalent clean air approach, I think, is getting some acceptance and has a lot of things to recommend it. Performance approach based on quantified harm or benefit is a good thing, and given that we have sensors that are now better able to support it. The evidence that a small number of contaminants need to be controlled, with PM being number one, is encouraging. If we just do a good job on PM in our buildings, we've really improved things a lot. And I think the growing potential for air cleaners to do more of our indoor air quality control is a good thing too. We may actually be able to reduce outdoor air from prescriptive levels in some cases if we do it appropriately. And to enable that, the improvements in air cleaner testing are very important. But a little more. I couldn't get it on one slide, sorry. Needs and concerns. So I gave you the good stuff, the positives. Potential cost and complexity of performance standards is always going to be an issue. It's a lot easier to just do a little algebraic calculation using numbers from a table than to actually figure out how you could optimize. But I think we're moving in the direction where we can develop tools to help make that possible. There are some important gaps in knowledge or research that need to be filled. Air distribution is just a mess right now. We mostly ignore it in applying standards. Modeling of infection risk, we've done the best we could with our standards to date, but there are a lot of fairly uncertain parameters in those processes. Maybe, we will never get to total certainty, but I hope we can do better. And then need to know a lot more about air cleaner performance and safety. Harmonization of standards is a hot topic in ASHRAE. We're trying to actually get people from these different siloed ANSI standards committees to talk to each other. We've been in the same room together. We did a panel discussion on air change rates with somebody from 170, 62.1, 62.2, and 241 in Phoenix at our last meeting. So that's an ongoing project, and I think that will be beneficial as well. And finally, standards without enforcement are really kind of useless. So I think there's a need to identify what would be an appropriate level of regulation and enforcement and advocate for it, probably focusing in the US on the state and local level at the moment. And I think really important is post-occupancy evaluation of air quality. I think there's an analogy here to what's happened in energy, where reporting of energy performance data and putting penalties on buildings that don't maintain an appropriate level of performance is a good thing, and we can copy that in the indoor air quality world. So it's not quite lunchtime, and that's all I have. And so I'll end with the usual pictures of my cats to annoy Stephanie, because she's a dog person. Thank you very much. You need to go.
Question here. To what extent do you guys balance the inlet of humidity through ventilation against particulates and other indoor air quality issues when when outside air is the main strategy?
Yeah, I think standards for ventilation have not probably done as much as they should, but I don't know if Lou Harriman's here, but there's been a lot of talk about maximum indoor relative humidity or dew point that's allowable under ASHRAE standard 62.1. I think it's something that needs to be considered in the operation of economizers. Economizers in cool, humid climates can create really high humidity indoors that's bad in many ways, and low humidity and economizers can make really uncomfortable conditions and maybe create unhealthy conditions if it gets too low. But we don't do nothing, but we could do more. When I look at recommendations for humidity, I go to the ASHRAE handbook and the chapter on humidification, which has some recommendations which are pretty good, 30 to 60. 40 is better, but at least 30 to 60. And that's what I try to do in my home. I have humidifiers that I use to keep it above 40 in the winter, and I shoot for around 50 in the summer with the humidifiers.
So yes, I saw a couple of bullet points where you talked about sensor and sensor placement and sensor types in facilities who may be running under a BMS and have their HVAC system and dedicated outdoor systems on a DDC. Would your recommendation be that these sensors be placed downstream of air filtration on the return side and then also downstream of the mixing box so that you know that you're getting a good mix of air? And by sensor types, I mean not only just CO2 sensors, but other sensors that may measure VOCs or infectious aerosols, an X number of things that could also give sick building syndrome, not just CO2.
Yeah, well, if you're using CO2 for ventilation control, that's a hard one. You often measure the return. Return from a system isn't very good because now you're just getting the average, but return from a space is at least going to give you the average, but the variation can be very large. I imagine the CO2 concentration is quite a bit lower where I'm standing than in the middle of the room. So how many sensors and where do you put them is going to be an issue. But I'm more concerned about what is the level of the contaminants that I'm trying to control in the occupied space. You'd want to know what's in the outdoor air, because if you're going to use potentially more outdoor air, then you've got to know what's in it, the ozone particles, whatever it might be that is a problem in that location.
Thank you for that. I've been
Sure.
trying to ask that question for colleagues, and it's always something that they can't answer always right away. So thank you for that.
Mhm.
There's a lot of good sensors out there on the residential market that read particulate matter, VOC, CO2, radon, formaldehyde. Obviously, humidity is a factor. If demand control ventilation has been accepted in the commercial standard, why not include it in the residential standard if the technology is there to do the same thing?
Yeah, why not? But you got to measure more than CO2, right? You got to look at PM, and you've got to look at humidity, and you've got to control all of those to be acceptable. The thing with VOC measurements is a TVOC is a pretty worthless measure. You saw in the papers that I presented that formaldehyde is really the bad actor. You can have a high TVOC level that's not causing you really any risk because it's something benign, or you could have what looks like a fairly low level and you've got a real problem. So I've always been kind of averse to buying an air quality monitor because I hate to spend money on something that has a TVOC sensor in it. See.
Thank you for that great presentation. I noticed a kind of glaring silence on mold and mycotoxins and non-infectious biologicals. And I think obviously the common consensus is to not have mold, but generally we find that most residential homes have some level of mold. I was wondering if you could just comment on that.
Yeah, well, of course, I mean, from my point of view, controlling humidity is the first thing you need to do. And making sure there's not water coming in through the enclosure, which isn't really a ventilation problem. Yeah, I mean, Joe has pioneered showing how, like a bad envelope combined with a poorly installed HVAC system can create a real mess. So, but, I was really just talking about the standards, and I think controlling in the space, humidity levels is one thing, but the interstitial spaces, I don't know what we can do about those if the building's not put together right.
Yeah, and kind of like the shit happens factor, like there's always some plumbing thing or whatever.
Yeah, but there's some interesting stuff, and I too many topics to talk about in 90 minutes. I'm involved in a project called ARPA-H Breathe that is going to be a 5-year project, and there are, I think, 4 or 5 different teams working on real-time biosensors that ultimately are supposed to be able to identify at least, I think, 25 different bioaerosols, and we're not just looking at pathogens, it's also allergens on those teams. So we hope that technology is coming, and that's supposed to be integrated into a risk model and field tested to see whether we can actually control using the input from those sensors.
What is that?
ARPA-H, it's kind of like DARPA, ARPA-H, and the specific solicitation is breathe. Mhm.
Doctor, thank you for the presentation. I thoroughly enjoyed it. Qualitatively, while the battle is not raging right now between pleated filters and electronics, do you have any sort of just qualitative comments on the electronic, the 20,000 volt plate and wire filters compared to that of pleats?
Well, I think ESPs can be a good technology, and you saw that it actually performed quite well in that byproduct test. So, I think they have their uses. I'm not sure what the cost factors are between using mechanical filters and having electrostatic precipitators. Anything, though, with a corona discharge, potentially going to be a source of ozone that could be a problem. So I'm happy to see them used as long as they're appropriately tested and qualified. But it is good technology, and charging particles has been shown to improve the performance of mechanical filters as well. So I think there's some good potential there, not just electrical potential.
Hi, thank you for bringing some clarity to these important topics. I appreciate that very much. My question for you is, do you have an opinion on building control services such as Passive Logic, BrainBox AI, and Sendle Breathe to take the human operational component out of thermal comfort and ventilation control?
I don't have any really specific comments, but I think, I gave a talk on Are We Smart Enough for Smart Buildings a few years ago. And one of the things I found by doing the literature search on that was that, we'd kind of gone full circle to we're going to do everything automatically to putting the human back in the loop a little bit. And so that's kind of, I thought that was a persuasive argument. I really don't want to have something that was designed by somebody I never met who doesn't know me controlling my building. I'd like to have some ability to interact with it.
So about 25% of my work is resolving problem projects or rescue projects. And I see that the lack of maintenance or that building engineer having to do manual adjustments causes more problems than it solves. So that's why I mentioned it.
Well, yeah, maintenance, of course, is an issue in itself. And of course, we've talked about that here, right? They came in to maintain the air handling units, and then now we're set back to where we were.
I'm talking about more of the measurement adjustments and just because it's antiquated. Thank you.
All right, this will be the last question, but you can catch them personally. So you're it, then we're going to eat.
Thank you, Bill. Quick question, like your thoughts or comments on on the residential side, on the building air leakage from the International Mechanical Code or Florida Mechanical Code. They say you need mechanical ventilation if you're at 3 ACH or less. And you spoke of the credit that you can get for infiltration, from on the ventilation standard. You also mentioned the 5 ACH was good acceptance. If you could speak a little bit more on the 5 ACH and where that came from and where that resides, and just your thoughts on 3 ACH and where it came from.
Yeah, the 5 ACH came from a dark place. CDC got a lot of pressure from the White House to come up with a number before the COVID restrictions entered in March of 2023. They couldn't just wait for us to finish 241. So like at the same time, CDC, and one of the guys who had to say, okay, it's 5, is the chair of the air cleaner subcommittee of 241. So there was that. The method in 62.2, you can take credit for whatever leakage you've got, and the rest has to be mechanical. Yeah.
So the three came from Sweden. Serious, it was in the Swedish code. And what happened is that in Canada in 1982 under R2000, we divided it in two because we thought we were twice as good at hockey as the Swedes. So that got us to 1.5. But I'm serious. We just simply took 3. We're better than the Swedes. We divided it by 2. Now at the same time, the Small Homes Council in Champaign-Urbana, Bill Bahnfleth, built the locale house, which was less than
Bill
one.
Rose.
Sorry, Bill Rose. Wayne Schick.
Yeah, way
Schick.
back.
And it was at less than 1 ACH at 50. And then it was adopted, the technology for the double wall was stolen by a bunch of Canadians in Saskatoon, and they built 8 houses that came in at 0.6 ACH at 50. And I was asked to build 1,000 houses at that number. You have any freaking idea? You know, if you build a square, ugly box with nothing, you'll get there. And so we test built 100 houses, and was lucky for us to get to, you know, just over 2. So we simply then multiplied that by 2 to get back to 3. No, I'm serious. And then what happened was, you know, several decades go by, and then we built under the Building America program with some of the production builders. We built and measured 1,000 houses in Chicago, and found that, you know, if you got rid of the big holes, you could get below 3. And so we ended up. Well, no, but you know, and why, you should ask why 50 pascals. You want to know? No, we're talking tightness, right? Yeah. He's nodding. He's talking tightness. Yeah. And you know, anyway, but so okay, where'd the 50 pascals come from? Well, I didn't have a fan big enough to get to 75. Because my original contract was to get to 75.
And where did the 75 come from?
I'm going to tell you. So I wanted to know, so I went up to the National Research Council of Canada, was talking to Gus Hanegard, one of our mentors, and I said, Professor, I always wanted to know where the 75 came from. He says, come with me. We go to the corner of the director of the Division of Building Research, and he says, Joe wants to know where the 75 pascals comes from. And the head of the department of building science said, I didn't have a fan big enough to get to 100. So the original plan was 100 pascals. We couldn't do it. I couldn't get to 75, and I got to 50. And so a couple of years go by, like several decades, and I go to the committee and I say, well, look, we should maybe go back to 100 pascals because the noise is going to be less, blah, 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 blah. And they says, no, there's a lot of research that went into where we got this. And I said, that's why it's called BS. All right. Anyway, thank you.